Last time, we left off wondering why some paths on our w-plane led us to completely new values on our z-plane, while others didn't. Gauss's student, Bernhard Riemann, made some powerful insights into problems like this in the mid-19th century. The first part of Riemann's contribution is the idea that for problems like this, we need more than two complex planes to visualize our function. Since each point on our w-plane maps to 2 points on our z-plane, we can begin to resolve our ambiguity by adding a second w-plane, and letting each of our 2 points on z map to its very own copy of the w-plane. So that's fine, but it immediately raises an important question. How do we pick which z values to map to each plane? A simple and effective approach here is to simply divide the z-plane into 2 halves. We'll let the right half map to our first w-plane, and the left half map to our second w-plane. These restricted versions of our multifunction are called branches. Let's draw a path again, but this time just on our first w-plane. Things look just fine until we cross the negative real axis and our path on the z-plane suddenly jumps. This, of course, is what must happen. We've required points from our first w-plane to only map to the right side of our z-plane. Almost every point on w has 2 possible solutions on z, and with our first branch, we've decided to always pick the one on the right. So our path now jumps around the z-plane. But what's perhaps more disappointing here is that we haven't gained any insight into our interesting loop behavior we saw last time. In fact, we can't even recreate this setup. No matter what kind of loop we draw, we always end up exactly where we started on both the z and w planes. It seems we've legalized this behavior out of existence. Further, the fact that our function jumps across the z-plane means that our branches are discontinuous, a huge problem mathematically. Functions of complex variables are a big part of modern mathematics and science, and if our functions are jumping around like this, we can't do important things like take derivatives and integrals. So we fixed the multi-valued problem by splitting our multifunction into branches. Our function is now 1 to 1. But in the process, we've introduced some serious issues. Thus far, Riemann's solution is not looking so great. Fortunately, that was just part 1, and part 2 is much cooler. Let's consider our discontinuity problem in a bit more detail. We'll switch back to our forward function momentarily, and again draw on our z-plane. Let's pay careful attention to where our discontinuities show up. We'll follow the points along a single path, and to make sure we can tell our points apart, we'll continuously change the color of our path. As we move from quadrant 1 to quadrant 2 on z, we switch branches. We switch back to our first branch when moving from quadrant 3 to 4. For our path to be continuous, we need to somehow connect our 2 w-planes at the exact points where our path jumps. What Riemann saw here was a way to bring together our 2 complex planes in such a way that our multifunction would be perfectly continuous, while maintaining the nice 1-to-1 properties of our 2 w-plane solution. Our next step is to grab some scissors and tape. We'll figure out what to do with them next time.